Welcome, students. So we are going to discuss today about section 1.3, which is classification of differential equations. So this code becomes very valuable as a lesson. I have yet to see any problem, however complicated, which when looked in the right way, did not become still more complicated. So the idea is you have to look at the problem from the right perspective, and then you're able to solve it. Similar thing goes about differential equations as well. Now, there are different types of differential equations, and each of those types will need some kind of technique to solve them. And one technique may not apply to all kind of differential equations. So it does make sense to classify the differential equations, classify into different kind of differential equations. Now, what are these different quote unquote kind of differential equations? So we'll classify them based on three things. One is the type, order, and linearity. Okay, so let's investigate each of this, what these words mean, and what do we get out of that. So what is an ordinary differential equation? So most of our course, actually almost everything about our course is related to ordinary differential equation. So what is an ordinary differential equation? So a differential equation of type, say, let me give you an example. Differential equation dy by dt equals to e to the power t plus y. So this is an example of an ordinary differential equation where t is the only independent variable. So you have d by dt. So the idea behind the ordinary differential equation is there is what the unknown depends on one independent variable. Yeah, so we are looking at derivative with respect to t. In contrast to that, we have what is called as partial differential equations. So partial differential equations. So in partial differential equations, the unknown or the function for which you're trying to solve, for example, depends on several independent variables. For example, dou square u by dou x squared. So this is partial derivative of u with respect to x. So second order partial derivative equals to partial derivative of u with respect to t. So where you have your u is a function of both x and t. Or another example could be you have, let me give another example, say uxx plus uyy equals to 1. Yeah. So you have the second order partial derivative of your function u with respect to x, and second order partial derivative to y equals to 1. So in our course, although we may see some partial derivatives, you'll see them usually when you are doing either the exact equation or you're dealing with the existence and uniqueness of solution to differential equation. We'll come to that later. But we will not we will not attempt or solve partial differential equations, or in short, PDEs. Okay, that is not our interest. For that, you have to look at the next course. All right. So this is the first classification based on type. Now, there are what are called as system of differential equations. So what is a system of differential equation? So this occurs when two or more differential equations have what? Mutual dependencies. So let me give you an example. The example comes from the Kepler's law of planetary motion. So let Q of t, which is denoted by Q1 t, Q2 t, and V of t, which is V1t, V2t, be momentum, be position, and momentum vectors of the moving planet in a solar system consisting of two bodies. Now, the idea is basically, say Q1 will represent the position of, say, in our case, if we only consider Sun and Earth and forget about every other planet in the solar system. So if you consider this two bodies in the solar system, then if Q1 represents the position of Sun and Q2 represents position of Earth, and V1 represents the momentum of Earth, and V2, sorry, of Sun, and V2 represents the momentum of Earth, then they are related in certain way. Okay, so what is a relation? So sorry, generally the momentum is given by P. So let's keep P. Although P equals to m mass into velocity, so you can manage that, but let's just keep P. So P1t times P2t. Then the relation between these two guys is given by what is called as Kepler's law. So Kepler's law tells us the relation between the position and the momentum. Namely, if you take Q1 prime t, Q prime t, which is basically derivative of this vector, which amounts to taking derivative of individual vectors, sorry, individual components of the vector. So note that this is going to be Q1 prime, Q2 prime, right? So this is equal to P of t, and we have P prime t equals to -1 by Q1 square plus Q2 square to the power 3 by 2 times Q of t. So this is a connection between what? The position and the momentum. And if you try to draw this under certain constraints, you'll see that a nice ellipse will come out. Okay. So you would see if you do Macam 316, in that when you try to plot the solutions to this numerically, you'll find a very nice ellipse coming out of it. Okay. We'll see this in more details when we are doing chapter 7, but for now, we are just introducing it. So this is good enough as an introduction. Okay. So now the next thing, so we have already done the classification based on type. So it's either ordinary or partial. The next type of classification is classification by order. So what does it mean by order? So note that this is dy by dx is the first order derivative, right? The first order derivative. D cube y by dx cube is a third order derivative. Now the order should make sense. Now, order of differential equation is the order of the highest derivative that appears in the equation. Okay, so let's look at the first one. So let's look at the derivative term. So we have dy by dt equals to ay plus b. So the derivative which appears is dy by dt. And what is the order of this derivative? It's 1. So therefore, this differential equation is of order 1. Order 1. Yeah. So I should say differential equation of order 1. Of order 1. Now let's look at the next one. Y double prime plus 10y prime plus 2ty prime equals to e to the power t. Let's look at the derivatives. So these are the derivatives. Now what is the order of highest derivative? 2. So this guy is second order differential equation. Now let's look at this guy here. So if you look at this, you have this thing. So this one will be order 4 differential equation. You may say, oh, is it order 6? No, there should not be any space of confusion for that because you're multiplying the two derivatives. You're not taking the sixth derivative of this, right? The highest derivative you have taken is a fourth order derivative. So this is order 4 differential equation, right? Now, again, let me remind you, why are we doing this classification? We are doing this classification because the techniques for solving them becomes easy. All right. So every differential equation has every, for example, based on the order, there are techniques to solve differential equation. Yeah, combining all these orders will help us to look at the techniques of differential equations to solve them. Now, next basically is the following. Now let's look at the following. So what is the general form of differential equation? So we can express an nth order differential equation. That means it has an nth order derivative inside it. So we can represent nth order ordinary differential equation in the following form. You can write it as f of x, y, y prime, y double prime, all the way until nth derivative of y equals to 0, where your f is a function of x, y, y prime, y double prime, all the way until nth derivative of y. Let's see an example. So let's just convert some of these. So how do I write this guy in the general form? So I can write this in the general form as follows. So I have fourth derivative of this guy times second derivative of this plus 2y y prime equals to t. And in general form, what you can do is you can bring this guy on the other side and bring that here. You get what? Y plus 2y y prime minus t equals to 0. And this is your f of y second, y prime, y, and x. You may say, oh, well, what about y3? There is no third derivative of y3, but still we need to write it like that because the coefficient of that is 0. So This is writing the differential equation in the general form. So this is the general form of the uh, ordinary differential equation. However, we can also write it in a second general form, in which what we'll do is we will keep the highest order of derivative on one side and move everything on the other side. So for example, you have yn equals to f of x, y, y prime, y double prime, blah, 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 yn minus 1. So if I want to write this differential equation in this form, what will I do? I can basically say my fourth derivative of y plus second derivative plus 2y y1 equals to t. Now I want to isolate this guy, the highest order. So this can be done. Yeah. So this is a second general form. So we'll usually write the differential equation in the first general form or second general form. Okay. So now comes the next classification. So we build all this form, general form, to understand the next classification. So we did two classifications already. The first classification was classification based on type. Second, we did classification based on order. And the third one we are interested in to talk about is the classification based on linearity. So let's move ahead and let's do the classification based on linearity. So suppose I write my differential equation in the general form. So this is a function, right? This is a function, capital F is a function of t, y, y prime, dot, 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 nth derivative of y equals to 0. Now this differential equation is called linear if f is a linear function of y, y prime, dot, 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 y n. Okay. If that is a linear, if this is a linear function of these guys, then we say that differential equation is linear. All right. Now, what does it mean by being linear? It means that you will have a0 t y n derivative plus a1 t yn minus 1 derivative dot 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 a n t. These are these are some functions of t, okay? Y minus g of t. Now the idea is none of y, so neither no power of y or the derivatives of y have power more than 1. Yeah. For example, you don't have y square there. If there's a y square inside this, or if there is a y double prime square inside that, then it will be nonlinear. Okay. So every power of these guys, you can notice, is what? Power of these guys are 1. Okay. So that's why we call such a differential equation linear differential equation. And if above is not the case, then we have a non-linear differential equation. So let's do the classification. X prime equals to e to the power tx plus t square. Yeah. So let's see, is it first order linear differential equation? Let's see. So we have f of, so t is the independent variable, x is the dependent variable. So look at x prime. This is going to be what? If I arrange everything on one side, I can bring it as x prime minus e to the tx minus t square. This can be seen as x prime a0t plus a1t of x minus g of t, where a0 is 1, a1t equals to minus e to the power t, and g of t equals to minus t. Sorry, we are writing it in the minus g of t format. So this is going to be g of t is going to be plus t squared. So you see all powers of x, x or x prime is 1. So therefore, this is a linear differential equation. Right. Now let's look at this one here. The question is, can it be written in this format? If it is, that's a linear differential equation. Otherwise, it's not. So look at y double prime plus y prime equals to t. Now this makes it what? Because of this, now y should have been separate. The only thing which you are allowed to multiply with y is some function of t. But you have y and y prime multiplied together. This is what? Non-linear. What is the order? Second order. Why? Because the derivative is of second order. Similarly, for first order, for first one, we should have also written this.
So first one is first order.
Third one. So let's see. So here we have, this is the third order. Is it linear? Now think about it. If it just had x, it was okay. But instead of that, it has a sine x. This is a non-linear function. This is a non-linear function of x, right? Non-linear function of x. Therefore, third order non-linear differential equation. Okay. So this is the classification based on A type. So all these are ODEs, ordinary differential equations. So the type is ordinary differential equation. What is the order? As you saw, the first one is first order, second one is second order, third one is third order. All right. And then the next one is linearity. So the first one is linear, second one is non-linear because of multiplication of y prime, and third one is also non-linear. Okay, because of sine x. Sine x is not a linear function of x. So this does the classification based on linearity and non-linearity. All right. Now the question is the following. So we have done the classification. Now let's also fix what does it mean to find a solution to a differential equation. Now, if you're given a differential equation of the following form, f of t, y prime, blah, 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 nth derivative of y equals to 0. Note that this is a general form of differential equation. What does it mean by solving this differential equation? It means basically finding a replacement for function y. So in other words, so this differential equation has a solution on certain interval I. It may not be whole of real numbers. It could be just small part of a real number. So it has a solution on interval I if there is a function phi, which is of course phi of t, function phi of t, that has at least nth derivative, which satisfies what? F of t. Instead of y, I have phi of t. Instead of y prime, I have phi prime of t. Instead of y double prime, I'll have phi double prime of t. All the way, instead of y, nth derivative of y, we'll have phi n of t equals to 0 for all I in t. So this will correspond to your solution of differential equation. Okay. So now consider the following differential. So show that this is a solution. And y prime equals to ty prime minus y minus t square equals to 0. So now to check that phi t is a solution, you have to basically, instead of y, take phi of t and see if it becomes 0. So let's take that. So f of t phi sorry, I should have included y here as well. Y prime. F of phi t, phi prime of t is going to be t, wherever there's y, I need to use y prime or phi prime of t. What is phi prime of t? Let's do that. Phi prime of t is 3 plus 2t squared. So we get t times y prime, which is 3 plus 2t minus y, which is going to be, y is, instead of y, I'm having phi of t, which is 3t plus t squared minus t squared. And see what do we get out of this. So this is going to be 3t plus 2t squared minus 3t minus t squared minus t squared. So 3t and 3t get cancelled. 2t squared minus t squared also get cancelled. So you get 0. So indeed, so therefore, phi of t is a solution. Now note that generally verifying a given function as a solution of differential equation is always, almost always easier than finding the complete set of solution. All right. And you will see how sometimes just finding the solution by inspection itself gives you a lot of leverage on solving differential equation. So we'll see that later on. So I think this is it. Thank you for your attention.